When it comes to machine learning, there are lots of different flavors you can implement. One of the most common strategies is regression. Regression machine learning is a style of supervised machine learning, and that means that you can train the model with data that already has the answer. Basically, what we want to do with regression models is we want to be able to predict values based on the features of our data. For example, imagine you wanted to create a model that could predict the price of a car based on the characteristics of that car. Well, you would first feed data into the model trainer that tells the model what the price of the car typically is based on a set of known characteristics. And in the end, once you've trained the model, you can set about predicting labels for new data sets where we don't know the answer. In Azure, you can use machine learning tools to create regression models. It's pretty straightforward, too. Since regression models are so common, most of the tools that you need are already built in. In other words, you can create regression models on your data without ever having to write a single line of code. Now, the tools in Azure, particularly in Azure ML Studio, are all drag and drop. So you can add whatever modules you want to manipulate your data or alter how the model gets trained. Now, not all regression models are the same. There are lots of different flavors of regression. So Azure allows you to choose which particular algorithms you want to use on your dataset to train your model. For example, Bayesian linear regression is probably the simplest regression strategy. It uses a linear regression strategy, but it's geared towards smaller datasets. There's also the boosted decision tree regression strategy. This uses a bunch of regression trees together. The term boosted means that each generated tree is based on the last, and that typically means that you get a very high accuracy in the results. Then there's the decision forest regression. Now this is the same as the boosted decision tree strategy, except that each tree is not dependent on the last one. Now the fast forest quantile regression is a good strategy to use when you want to get more information about the distribution of the predicted value, rather than getting a single predicted result. Of course, there's the standard and extremely common linear regression strategy too. And neural network regression allows you to create your own custom regression strategy. The ordinal regression strategy can help you predict, unsurprisingly, ordinals. And finally, the Poisson regression strategy is really good for predicting numerical values like counts. So let's take a peek at each of these in graph form. First, we have the Bayesian linear regression. Now remember, this is the same as linear regression except for smaller datasets. But it works the same way. We can plot our data on an XY chart and then we can draw lines that fit best with that data. This is how linear regression works too. We might try different lines, but the one we use is called the true regression line. Then we have the boosted decision tree regression strategy. In this case, we're building decisions on top of each other. So we can make a decision about a piece of data, then, based on the results of that decision, we can make another decision, and another, and so on. Each decision leads to a new decision that ultimately leads us to an answer. Then it becomes a game of Plinko. Each new data value goes through the decision tree based on its particular characteristics. Now, the decision forest is similar, but not the same as the boosted decision tree. In this scenario, we build many different and unique decision trees. Whereas the boosted tree had one big decision tree, the decision forest has multiple trees. So each new data value goes through all of the trees. Then each of the results is averaged or voted on based on majority, and the result is output that way. Now the fast forest quantile regression strategy is about using data distribution to arrive at answers. So in this chart, we can see a chart of violent crimes over a certain number of weeks. For each week, we put the data into quantiles. Now, each quantile is then averaged for that week and charted. And this lets you see where the spikes are in your data and where there aren't. You can also use the information from each of the quantiles to get a better understanding of where you really are. So back to the chart, as an example, you could draw a line of best fit through this chart and you get a pretty decent idea of the number of violent crimes you get per week, while effectively ignoring the spikes around weeks 100, 200, and 300. Next, we have our standard linear regression, and this is probably the single most common strategy implemented. certainly by early adopters of regression-based machine learning. Put overly simplistically, linear regression is about drawing a line of best fit through your data when plotted on an XY chart. That's overly simplistic because most models have lots of data that need to be evaluated for correlation. But way down deep in the heart of the strategy, we're determining the true line of regression for various data values. Now, the neural network regression strategy allows you to do all sorts of custom algorithms with your data. Neural networks are generally used for deep learning complex models like image recognition. They can be easily adapted to deal with all sorts of regression problems, and technically any type of statistical model can be called a neural network. The main identifier of a neural network is that they use adaptive weighting and perform nonlinear functions on their inputs. So you can have a bunch of layers between your inputs and your eventual output as long as each layer has some weighting and applies a nonlinear function. All that means is that neural network regression is really good for problems where a more traditional regression strategy simply won't do. Now, ordinal regression is generally used in situations where your input data is based more on ranking than actual measurements. For example, if you wanted to perform regression analysis on a baseball player, then you can apply linear regression on their statistics, like number of home runs, say 20 home runs. But you'd use ordinal regression if you wanted to use their statistical ranking, like they rank 5th in the league in home runs. And finally, you have the Poisson regression. This strategy is generally used when the outcome you're trying to generate is less about a measurement than it is things like counts. For example, you could use Poisson to analyze a whole host of data and then determine the total number of illnesses that are associated to public transportation. Or you could predict the number of calls to 911 that typically happen during or after a sporting event. Now, which regression algorithm you choose will be totally dependent on both the data you have access to and the data you're trying to calculate. So choose wisely. So how would someone go about creating and training a regression model anyway? Well, the first thing you need to do is create a pipeline. A pipeline is where all the magic happens. It's where all the steps are defined, configured, and operated against. A pipeline is basically the recipe for your model. A model is only as good as the dataset it uses to train itself. So one of the very first things, if not the very first thing that you'd put into your pipeline, is a reference to your training data. But data is not always great out of the gate, so we can apply all sorts of transformations to that data and get it to the state where the model trainer requires it. And once you have your data where it needs to be and you've configured your model training like you want it, that's when you can finally execute your pipeline. And that'll actually train your model based on the data that came in. Now, once the pipeline is run, Azure will let you inspect the data that was generated at each step in the pipeline so you can inspect the input data, the transform data, and of course, the actual output data. So let's talk about each of these steps in a bit more detail. First, we have the pipeline creation. So as I said, pipelines are where the magic happens. A pipeline defines all the steps and various operations that you'll perform when you set about training a model. To create a pipeline, you'll need a bunch of modules to specify what those operations are. So you can include data manipulation, custom code modules, testing, scoring, evaluation, and of course, the actual algorithm that you'll use. So for a regression pipeline, you'd naturally pick algorithms like linear regression, boosted trees, Poisson, and so on. Now, in order to train a model or to execute a model, you need data, always. So virtually 100% of the time, the first step in a pipeline is the acquisition of data. The data can be a reference to an open data set, a reference to a cloud data store, or it can even be manually fed in by a user. Wherever it comes from, data is paramount, so it'll always be the first thing you want to make sure that you have. So why is data so important? Or more appropriately, what is it about data that makes it so important in a regression model? Well, the most obvious answer is that data is what's used to train the model to begin with. You can't just ask a model to predict the price of a car. It doesn't even know what a car is. And even if it did, the model has no idea what attributes of a car drive its price. When it comes to regression algorithms, you're trying to predict a value based on the characteristics of a dataset. In other words, you need data to predict data. So when we use the example of a dataset of cars, the dataset has all sorts of information about cars: number of seats, engine size, horsepower, miles per gallon, and so on. That information can be combined and analyzed by the regression algorithm to help predict a price. When you're training a model, the dataset would already include the price data so that the model trainer can determine the best model to match your data. But when you're running the model, the dataset would not have the price data anymore. Now, when it comes to training yourself, Microsoft has a whole bunch of sample datasets that you can use to wrap your head around the data that you're going to use in the process. The datasets can all be explored using built-in tools, and that lets you browse the data and get familiar with the quality of the data that you're feeding into the model trainer. Which leads quite nicely into the next thing that you do. Once you have data, you generally need to consider cleansing the data. Or put more appropriately, you need to transform the data. Data transformation is used to prepare data for the processing of model consumption. The idea is that you want to address any issues that you have with the data before you use it. For example, let's say you explored the dataset like I mentioned previously. While you were browsing the data, you noticed invalid columns, missing data, and wildly different scales of data values that you would consider to be equally important. Well, with data transformation modules, you can take that input dataset, remove undesired columns, remove undesired rows, and normalize certain columns to the same scale to reduce bias during training. There are lots of different transformation modules that you can use, and the worst case scenario is that you can use a custom code module to adjust the input data to exactly the format you need. So it's really quite flexible. So once you've got your pipeline to where you want it to be, the next thing you do is actually execute the pipeline. Executing the pipeline means that all the modules you chain together in the pipeline will be executed in the order that you prescribe, and the outputs will be generated based on the provided inputs. So the first thing that's done is that the connected input dataset is retrieved from wherever the source is. And once the data is collected, whatever transformation modules were defined are then run in order. So in my previous example, that could be modules that remove unwanted columns, remove or adjust unwanted rows, and finally normalize some important columns to the same scale. Now once the data is in the state where you need it, the rest of the pipeline executes. At that point, you just need to wait for it to complete. Now the rest of the pipeline could be the actual model training, but it doesn't have to be. Sometimes people create pipelines that are just about data cleansing. Then they use that pipeline for data input to actual training pipelines. That can be very handy if you always have the same batch of transformation operations that you perform before your various model training pipelines. It means that you won't be repeating yourself by always putting the same bunch of modules in every single pipeline. Now, regardless, once the pipeline has executed completely, you're now free to explore the results. Each module that touches input dataset can be explored in its raw state, but then the output of each of the transformation modules can be explored too. So going back to my example, that means we can see the dataset after it's had a column removed, then we can examine that dataset after it's had its rows removed, and then we can examine that dataset after it's had a bunch of its data normalized to the same scale. Of course, it also goes without saying that you can also view the output of the actual trained model. If you have scoring and evaluation modules, then each of those can also have a dataset that can be explored. So how do you do that? How do you explore a dataset? Well, with Azure ML Studio, each module offers you two methods to get to the Data Explorer. First, you can select the module and a panel will appear with the dataset inside it. That dataset includes a button that allows you to click and visualize the data. Or easier still, you can right-click on the module and select to visualize the data right there. The visualizer pops up in a dialog that allows you to see the dataset itself as well as little histograms for every column of data, and we'll see that a little bit later in the course. Training models is not a simple process. You need to really understand your data and what you're trying to get out of it. That means making sure you choose the right number of independent variables. The data you have in your model's input dataset is imperative in training the model. If the data is junk, the model is junk. Likewise, if you don't have enough variables, you can get an underspecified model, and that can result in bias. For example, imagine you wanted to predict the price of a car, and the only data you had in your dataset was miles per gallon and horsepower. Well, naturally, your model would put huge emphasis on horsepower being the driver behind the price of the car. But you and I know that's not nearly enough data to make that determination. Likewise, the data that you use to train a model needs to be meaningful. So you can swing the pendulum the other way too. If you give your model too many features, you can have an overspecified model, and that can result in a lack of precision. So again, in our car example, I could have a data set that lists everything about a car down to its nuts and bolts and the manufacturer of the upholstery. Now, most of that data wouldn't make too much of a difference in the price of the car, yet they would add weighting to the model, and you probably don't want that. At the end of the day, you want to find the sweet spot. You want to have the correct terms that we know or suspect are contributing factors to the outcome. We don't want any bias, and we want the model to be as accurate as possible. But how do we know a model is accurate? What are some of the ways that we can evaluate our regression model output to determine if it's done a good job at predicting a result? Well, the good news is that there are a certain set of metrics that Microsoft can give you to evaluate your regression model outputs. For example, one of the most common metrics is the R-squared metric. This metric summarizes how much of the variance between the predicted and actual values can be explained by the model. Now, this metric is a value between 0 and 1, and the closer to 1, the better the model is at making its prediction. For example, we all know that when a person gets pregnant has a direct relation to when they give birth. In that case, we could make a prediction that a baby will be born on such and such a date. As a society, we've gotten pretty good at making that prediction, so our R-squared is pretty close to 1. Next, the mean square error metric is the average squared difference between the predictions and the actuals. The root mean squared error metric is similar, except that it tells us the square root of the mean squared error. In both cases, the metric it produces is a positive value between 0 and 1, where a value closer to 0 is good. Basically, a value closer to 0 means that there was very little error in your prediction. So, again, if we can predict exactly when someone will give birth, we will have very little error in our prediction. And next we have the mean absolute error value, which is the average difference between our predicted and actual values. This value is measured in the same units as our predicted value. So if we go back to our example about predicting the price of a car, this value would be in dollars. And if our predictions were exactly accurate, our mean absolute error would be $0. But since we know we'll never be exactly accurate, this metric will tell us how far off we are from the average. Now, another mechanism for evaluating your model is to produce the p-values for your independent variables. The idea behind p-values is that they can tell you the significance that they played in producing a result. So any variables that had a bad p-value, meaning that they were insignificant, can be removed from the model to make it more efficient and hopefully more accurate. And finally, you can actually play with the algorithms that will automatically determine which variables you might want to use in your model. Algorithms like stepwise and best subset can run various versions of your model with different inputs to see which ones give the best results. Basically, they work by trying to find the right balance between precision and bias. So that's a lot of different metrics that are available to you, but which one or which ones should you use? Well, that's going to be based on your situation and even your individual comfort level. Now, R-squared is extremely common and generally the easiest to describe, so it's a really good idea to start there. A value closer to 1 is good and a value closer to 0 is really bad. And that's pretty easy to wrap your head around, right? Well, going back to our example about predicting when a baby will be born, if your R-squared value is 1, then you know that you predicted the date of birth exactly right. So if you're just starting out and you need to explain the effectiveness of your model to yourself or to others, R-squared is a good bet. Now, to make things even easier, there's a specific Python library for calculating R-squared metrics, So you can even run tests and further calculate additional metrics if you want to. Basically, you can make this as easy or as complicated as you want. Now, you can also use the adjusted R-squared value to account for overfitting. Now, overfitting happens if a model has too many variables and starts to model random noise into the output. That can actually lead to a misleadingly high R-squared value. So that's a good next bet for you once you get comfortable with R-squared. And finally, once you're more familiar with models and the metrics that they produce, looking at the mean squared error, root mean squared error, and mean absolute error metrics is a good next step. They can give you really good insight into the effectiveness of your model. In this demo, we're going to create a pipeline in Azure ML Studio to prepare a dataset to be used in a regression pipeline. To do that, we're going to create a new pipeline through the designer, and then we'll add and configure certain modules to bring a dataset inside and cleanse its contents. We'll know it's working if we can execute the pipeline and inspect the data. First, we need to access the ML Studio from our browser. So what we want to do here is we want to author a new pipeline and play around with some modules and how they would connect with each other. To do that, we need to access the designer section from the left-hand menu. So let's do that. Now the designer screen shows us a list of all the pipeline drafts that we already have. In fact, that's what the designer is doing. It's giving us the ability to manipulate pipelines and how they run. So what we want to do here is we want to create our own new pipeline. To do that, we can simply click on the giant plus button at the top of the screen, and this will bring us to a brand new pipeline. So let's do that. Perfect. So now we're in the designer, and we have an empty canvas right in the middle. And there's a list of modules on the left-hand side. And there's some configuration information about this pipeline on the right-hand side. In fact, the right-hand menu is already asking us for some information about this pipeline, so let's do that first. We can do that by clicking on the Select Compute Target link, so let's do that. Now in the pop-up, we're asked to select a compute cluster to use for this pipeline, and that's important. If we run this pipeline, it will add that run to an experiment, and all experiment runs need to be done using a compute cluster. So with this dialog, we can select an existing compute cluster or even create a new one. But to save time, I'm going to select an existing compute cluster that I created earlier and then click Save. And now, using the same configuration panel, I'm going to name my pipeline something. Now, you can name your pipeline whatever you want, but I'm going to call my pipeline SB-Test Pipeline Demo. But I'm going to call my pipeline SB-Test Demo Pipeline. And then I'm going to click Save up top. Perfect. Now we're ready to go. Now, obviously, what we want to do is we want to build a regression pipeline. And that means that we want to train a regression model. But you can't do that without first bringing in some data to evaluate, right? So let's do that. Let's bring in some data to play with. In fact, we're going to use a sample dataset from Microsoft so that we can easily wrap our heads around that data. Now to get us started, I'm going to add that sample dataset to the canvas, and then I'll explain what we're going to do with it. Now under the sample dataset section on the left-hand menu, I'm going to find the automobile price data module and drag it onto the canvas. Okay, so this dataset includes a list of a whole bunch of cars. In fact, let's quickly explore this dataset so that we can see what we're working with. Right-click on the dataset module and select Visualize Output Data from the menu. Now in the pop-up, notice that there are 205 rows, and we'll need to remember that for later. The dataset includes all sorts of information about all sorts of cars. This includes things like the number of seats, engine size, miles per gallon, horsepower, and so on. And this is a pretty varied list of data, but all of it's important when you're evaluating a car. Now you can scroll through this data, but you'll see that some of the data is missing, that's the NAN values that you're seeing, and some of it is totally different scales than the other data. Now why is that important? Well, the regression pipeline we're going to want to run is going to try to predict the price of these cars. And it's going to use all of this data to do that. If some data is missing or some data is at different scales than others, then that might introduce bias in the result. So we have to cleanse the data before we can use it. So let's do that. Now first, let's close this pop-up. Okay, so in order to cleanse a dataset, we need to use what's called a transformation. In fact, we're going to use a bunch of transformations. The first transformation we're going to use is the column selector. This transformer will make sure that we're only using the columns that we care about. So in the left-hand panel, let's search for the Select Columns in Dataset module. Good. Now let's drag it onto the canvas. Excellent. Now we need to connect these modules. Now we want our dataset to flow into the transformer. So drag a connection from the bottom output dot of the dataset to the top input dot of the transformer. Nice. Now you notice that there's a little warning symbol on the transformer module, and that's because we haven't configured it yet. So let's click on the module to make sure that it's selected. Good. Now in the right-hand panel, click on the Edit Column link. Good. Now this pop-up is asking us to choose which columns it should care about. In actuality, we care about all the columns except for one. So let's click on the By Name radio button. Good. Now this is listing all the columns in the dataset. We want all the columns except the normalized losses column. And that column has lots of missing data, so we're going to want to ignore it. So let's first click on the Add All link at the top of the available columns list. Excellent. Now let's remove the normalized losses column from the selected columns list by clicking the little minus sign beside its name. Good. Now we can click Save. Awesome. So what we've done is that we've taken an input dataset and removed a column from it because it has lots of missing data. Except that one column wasn't the only one with missing data. So what we want to do now is add another transformer that decides what to do when it encounters missing data in some key columns. In order to do that, let's find the Clean Missing Data module. And let's drag it onto the canvas. Good. Now we'll connect the output of our existing transformer to the input of our new transformer. And once again, we see a warning symbol because we haven't configured the new transformer. So let's select the module and then click the Edit Column link on the right-hand pane. Now in this case, there are only 3 columns that we care about dealing with missing data. So let's leave the With Rules radio button selected. Now in the Include field, let's select the stroke, bore, and horsepower columns. Good, now we can click Save. Now with columns selected, we can then apply the rules of what to do when missing data is found in these columns. What we're going to do is we're actually going to remove the entire row from the dataset if missing data is found in any of these columns. So let's choose the Remove Entire Row option from the Cleaning Mode field. Great! So now we have a regular data set that flows into a transformer that removes undesired columns, and then flows into another transformer that removes undesired rows. That means our data set now only has the data that we care about. But now we want to transform the data itself. Remember how I said that some of the data has totally different scales? Well, if some data has huge numbers and some has really small numbers, a model might apply some unfair bias to the bigger numbers because they sway so much more than the smaller values. You know that these values are of equal importance, so what we want to do is equalize them, or more accurately, we want to normalize them. To do that, let's find the Normalize module in the left-hand panel, and then drag it onto the canvas. Good. Now let's connect the left output dot of the missing data module and connect it to the input dot of our normalizer. Now once again, we're seeing a warning symbol. So let's click on the new module and then click on the Edit Column link once again. This time we want to select a whole bunch of columns. Basically, we want to make sure that a bunch of the columns carry equal bias for our model. So let's do it. Let's click on the By Name radio button. And now let's add the following columns: symboling, wheelbase, length, width, height, curb weight, engine size, bore, stroke, compression ratio, horsepower, peak RPM, city MPG, and highway MPG. And now we can click Save. Now let's change the transformation method at the top of the panel to min-max. Perfect. So at this point, we've got a data set, and we've cleansed it using a few transformers. So let's see it in action before we start using it for our eventual regression model. Let's click on the Submit button at the top of the page. Now in the pop-up, it's asking us to connect our pipeline run to an experiment. Well, since we don't have any experiments yet, let's create one. Click on the Create New radio button. And let's give our experiment a name. I'm going to name mine SB Test Demo Experiment. Good. Now let's click on Submit at the bottom of the pop-up. Excellent. Now this kicks off the model run, and it might take a little while to run, so I'm going to fast forward to the end. Fantastic. Now that our pipeline run is complete, you can see that all the modules have been highlighted with a green bar and the word completed. But let's prove it. Right-click on the Normalized Data module and select Visualize Transformed Dataset. Good. Now, right away, notice that the Normalized Losses column isn't there. And there's also 199 rows now, whereas there used to be 205. And if you scroll to the right, you'll see that all of the columns that we selected to normalize are now in a shared range between 0 and 1. So that's it. We've prepared our dataset with nice, clean data. We're ready to run a regression pipeline. Great job! In this demo, we're going to build and execute a regression model training pipeline. To do that, we're going to piggyback off our last demo where we prepared a dataset. The purpose of our model will be to try to predict the price of a car based on its various characteristics. Okay, so the first thing we need to do is open the Azure ML Studio in our browser. Alright, now in our last demo, we created a pipeline, so let's open it back up. To do that, click on the Designer item in the left-hand menu. Now in the bottom section of the page, find your pipeline and click on it. Now mine was named SB Test Demo Pipeline, so I'll click on that. Good, now let's do a quick recap of what this pipeline is doing. So far, we've got a few modules on the pipeline canvas. The top module brings in a sample dataset from Microsoft that includes a bunch of data about a bunch of cars. The other modules are connected to the dataset after that to help cleanse the data in that dataset. Now these modules remove undesired columns, remove undesired rows, and then normalize a few different columns of data so that they have the same weight when it comes to feeding it into the model trainer. And that brings us to the task at hand. What we want to do in this demo is create a regression model trainer that's able to predict the price of a car. The eventual objective would be to pass in some data into an already trained model and have it tell us the price of what that car should be. Well, to do that, you need to first train a model with some existing data. Now, our dataset shows the model what the price of a car usually is based on certain characteristics. Now, the model learns from that data and is able to create an internal algorithm to help predict the price of the car in the future. So let's do that. Now, the first thing we need to do is actually something to help us test the model in the end. So the first thing we want to do is add a split data module. So let's find that module in the left-hand panel and drag it beneath our current stack of modules. Perfect. Now, what this module does is takes in some input dataset and splits it into two sub-datasets. Why? Well, what we're going to want to do is feed some of the data into our model training and then feed the rest of it into another module that will help us score how we did. But how much should we send? Well, let's click on the module to make sure that it's selected. And now in the right-hand panel, we can choose what the split will be and how it gets split. Now let's set the fraction to 0.7. Good. Now what that means is that 70% of the data will go to the first output and 30% will go to the second output. Now let's also set a random seed value so that it just doesn't start at the beginning. Let's set the random seed to something like 1, 2, 3. Good. Now we're ready to train a model. Now let's go back to the left-hand panel and find the Train Model module. And let's drag it onto the canvas slightly below and to the left of the split data. Good. Now let's connect the left output of the split data module to the right input of the Train Model module. Now what this does is feed 70% of our dataset into the dataset input of the model trainer. Now you notice that there's a little warning icon on our new module, and that's because it's not totally set up yet. So let's click on the new module to make sure that it's selected. And now in the right-hand pane, let's click on the Edit Column link. Now remember that what we want is for the model trainer to predict the price of a car. Well, we need to tell it to do that. So in the Column Names field, select the Price field. And now let's click Save. Perfect. We're now set up to predict the price of a car, right? Well, not exactly. You see, what we've done here is we've told the model trainer what to predict, but we haven't told it how to predict it. To do that, you need an algorithm. Now, regression models are great for training with numerical data and numerical outputs, and there are lots of algorithms that you can use. But for our purposes, we'll use a simple algorithm. Let's use the linear algorithm. Now, back in the left-hand panel, find the linear regression module. And let's drag it onto the canvas above and slightly to the left of the Train Model module. Perfect. Now let's connect the output of the new module to the left input of our model trainer. Good. Now we've got a regression pipeline that trains a model to predict the price of a car. Fantastic. Or is it? Well, to know the answer to that, we've got to test our model, and we've got to score our model. So let's do that. Now let's search for the Score Model module and drag it onto the canvas below the model trainer. Good. Now let's connect the model trainer output to the left input of our new module. So how does scoring work? Well, the module takes the trained model from our model trainer and applies it to another dataset. The input dataset should already have the right answer in it. Then the scoring module will check to see just how close the trained model came to that answer. If it's way off, that's a bad model and we should tweak something. But wait a minute, what input dataset? Well, remember our split data module? Well, now we can connect the right output of that module to the right input of our scoring module. That means we're going to use 30% of our cleansed dataset to score our model. So let's connect them. And let's align them so they look a bit better. Perfect. Now at this point, we've got a pipeline that uses a regression algorithm to train a model to predict the price of cars based on a cleansed dataset. We then take that trained model candidate and run it against part of our dataset that wasn't used to train the model and score the model. So let's run this and see what we get. Let's click on the Submit button at the top of the page. Now, in our last demo, we created an experiment. So let's just use the same experiment this time. Choose the experiment you used last time in the existing experiment field, and then click Submit. Perfect. Now our pipeline is executing. Now, that process may take some time, so I'm just going to fast forward to the end of the run. Excellent. Now our pipeline has finished executing. So let's select the Score Model module. And now notice that there's an Outputs and Logs tab in the right-hand panel. Now let's click on that. Mine's already open. Good. Now right at the top in the Data Output section, there's now a scored dataset object. Now on that object, there's a Visualize icon. So let's click on that so we can see the results of the model scoring. Perfect. Now in the pop-up, let's scroll all the way to the right. Now notice that there's our existing price column and that now there's a scored labels column. That's our predicted price. Now, if you scroll through the list, you should see some predicted prices that are reasonably close to the actual prices. Pretty cool, huh? Now, the prices will probably never actually be exactly accurate because there's lots of factors that go into the price. Sometimes you're just paying for brand names. Sometimes cars are more expensive because they're a fad. And sometimes cars are cheaper because the vendor wants to get them on the market. Now, the point is that while the algorithm can definitely be tuned for your specific situation, it's also equally possible that the model is showing some of the input data is actually flawed. Anyways, great job! In this demo, we're going to add an evaluation module to a regression pipeline in Azure ML Studio so that we can evaluate the results of a candidate model. We'll see how to add and configure the module in the pipeline canvas. And finally, we'll execute the pipeline and explore the results of the evaluation module. Okay, so the first thing we need to do is navigate to the Azure ML Studio using our browser. So in this demo, we're going to piggyback off our previous demo where we created a regression pipeline that trained a model on how to predict the price of cars based on a bunch of characteristics of those cars. So let's open that pipeline. Let's click on the Designer option in the left-hand menu. Now let's select our pipeline from the list at the bottom of the page. Mine was called SB Test Demo Pipeline. Good. Now we're presented with the designer. On the canvas, we've already got a set of modules that do a bunch of things. First, we have a sample dataset from Microsoft that includes a bunch of information about a bunch of cars. And then we run that dataset through a few transformers. The first transformer removes undesired columns, and the second transformer removes undesired rows. Then the last transformer normalizes a bunch of the data to the same usable scale so that we don't introduce bias into the model training. And speaking of model training, after the data cleansing, we feed 70% of the dataset into a model trainer, which is set up with a linear regression algorithm, and the other 30% goes to a model scoring module. So with what we built before, we can easily check the prices predicted by our model candidate against some real actual prices, and we do that with the scoring module. But in this demo, we're going to evaluate our candidate model. Just eyeballing predicted versus actual isn't really sufficient to really tell if a model is good enough. Now, configuring a pipeline to evaluate a candidate model is pretty easy. Actually, let's go over to the left-hand panel and search for the Evaluate Model module. And then let's drag it onto the canvas below our Score Model module. Now let's connect the output from the Score Model module to the left input of our new module. Perfect. That's it. Now let's run the pipeline by clicking on the Submit button at the top of the page. Now, in our last couple of demos, we attached our pipeline to a particular experiment. So let's do that again. Let's select the same experiment that we've been using. For me, I'll choose the SB Test Demo Experiment, and we can click Submit. Okay, so as usual, the pipeline may take a while to execute. so I'm going to fast forward to when it finishes. Perfect! Our model has executed successfully. Now let's explore the evaluation results. Now in the Outputs and Logs tab, notice that there is an Evaluation Results dataset at the top of the tab. So let's click on the Visualize icon to explore the results. Good. Now we're seeing a number of new statistics in this pop-up, and there's actually 5 statistics in here. The first is the mean absolute error value, which is the average difference between our predicted and actual values. Now ideally, the difference is none, so the smaller the value, the better our candidate model. Is this number good? Well, that depends. For predicting the price of buying a stadium, probably, but for predicting the price of a car, maybe not, although it's not too bad. The module also gives us the root mean squared error value, which is the square root of the mean squared difference between predicted and actual values. If this value is larger than the mean absolute error, it means that there's actually a greater variance in individual errors, and that's what we're seeing here. Now another value you get is the relative squared error. Now this is a value between 0 and 1, which is based on the square of the differences between predicted and actual values. Now this metric is good because the closer it is to 0, the better the model is doing, and this one's doing pretty good. Now a similar value is the relative absolute error. Now this is another value between 0 and 1, and it's based on the absolute difference between predicted and actual values. Now again, the closer the metric is to 0, the better the model is doing, and this one's not so good. And finally, one of the most common metrics is the R-squared metric. This metric summarizes how much of the variance between predicted and actual values is explained by the model. In this case, the closer the metric is to 1, the better the model is doing, and this isn't too bad. Okay, so in this case, we can take a look at our metrics and we can now make a more educated decision on how good our candidate model is. Now, personally, I'd say it's not that compelling and maybe could use a bit more tweaks. But how exactly would you do that? Well, there's a few ways you can do it. Maybe the algorithm is perfectly fine, but the data isn't good enough. We can fix that by sending in more data. Remember that we only sent in 70% of about 200 values. Or we can try to clean up the data that we have even more. And usually the answer is to add more data. A model is only as effective as the data it gets, and generally we're talking about millions of values. Now another thing you can do is actually tweak the algorithm. Now there are different kinds of algorithms and each of them have different variables that you can play with. So if the result isn't to your liking, there's lots more you can do. Now in the meantime, we've successfully run a model and we've successfully evaluated it. Great job. In this demo, we're going to create an inference pipeline in Azure ML Studio. To do that, we're going to piggyback off our last few demos and use an existing regression pipeline that predicts the price of cars. Now first, we need to navigate to the Azure ML Studio in our browser. So in this demo, we're going to piggyback off our previous demos, like I said, where we created a regression pipeline that trained a model on how to predict the price of cars based on a bunch of characteristics of those cars. So let's open that pipeline. Now click on the Designer option in the left-hand option menu. Now let's select our pipeline from the list at the bottom of the page. Mine was called SB-Test Demo Pipeline. Good. So here we once again are presented with our regression pipeline. So let's do a quick recap of what's going on here. First, this pipeline takes a Microsoft sample dataset as its input. The dataset contains a bunch of information about a bunch of different cars. Then we use a few transformation modules to cleanse the dataset to something that we can use. The first transformer removes some unwanted columns, while the second transformer removes some unwanted rows. And the normalization transformer adjusts the data for a bunch of columns to make sure that we're all using the same scale. Now this prevents any introduction of bias in the model training. Then we feed 70% of our cleansed dataset into a model trainer, and the remaining 30% goes to a module that scores the resulting model. So now what we want to do in this demo is be able to feed a new dataset against the model we just trained. To do that, we need to create what's called an inference pipeline. So let's go ahead and get that ball rolling. To create an inference pipeline, we need to click on the Create Inference Pipeline button at the top of the screen. Now in the drop-down, there's a couple of options. Now for us, we want to be able to test data sets on a sort of ad hoc basis. So we're going to choose the Real-Time Inference Pipeline option. So let's go ahead and pick that option. Perfect. So now what we've got is a whole new pipeline. And it's worth noting that this is pretty much the same pipeline as we already had, but with a few differences. First, you'll notice at the top of the canvas that there's a web service input module. And that's been placed right beside the dataset module, and they both feed into the next module. What this means is that this pipeline can now be triggered by a dataset sent in via web service endpoint. That's pretty fancy, and we'll get to that later. Next, you'll see our usual select columns in a dataset transformation module to remove the column that we don't want. And then there are the two apply transformation modules. Now this is just a different way to represent our removal of rows with missing data and our normalization steps. Next, we have the score model module, and this takes our trained model and applies it to whatever dataset is provided. And finally, the pipeline outputs the results to two modules. One is our evaluation module, so we can explore the results later on, and the other is a web service output module, so that we can return information to the consumer. Now, all that sounds pretty wild, right? Well, I'm going to make a few modifications to this pipeline to make our lives a bit easier. First, I'm going to rename the pipeline so that it matches my existing pipeline a bit closer. I'm going to call the pipeline SBTest Demo Pipeline Inference. I can do that by using the little cog icon beside the pipeline name and then typing the name in the configuration panel. And I'm also going to confirm the compute target is configured properly, which it is. Next, I'm going to remove the original sample dataset. That dataset that we used in our original pipeline was used to train a model, but it won't be needed when it comes to actually running in the future with real data. So let's just select the module and click the delete icon in the toolbar. Now what I do want is the ability to run this manually and to be able to provide data on the fly. Now to do that, I need to add a module for manual data entry. So let's search for the Enter Data Manually module and drag it onto the canvas where the original dataset was. And now let's connect the output dot to the input dot of the Select Columns and Dataset module. Now you'll notice that there's a little warning icon in the middle of the module, and that's because the module isn't fully configured yet. So let's do that. Let's click on the module to make sure it's selected, and mine already is. And now I'm going to copy and paste some CSV data into the data box. But don't worry, I'll include it in the doobly-doo so that you can use the same thing. Good. Now it's actually important to note in this dataset that we've provided that there's no price column. And that makes sense, right? Our goal is to predict a price. So once we put this model out into the wild, there'd be no price information anymore. But that also means that we need to make a modification to some parts of our pipeline. So let's click on the Select Columns and Dataset module. And let's click on the Edit Column link. Now, since price is not a column of information that we're going to be providing anymore, we need to remove it from the list. So let's find it in this list and then click the X to remove it. Good. Now we can click Save. Perfect. Now the next thing we want to do is remove the Evaluate Model module. When this pipeline is run by consumers, they'll have no real access or need for the evaluation module. So it's not really needed in this pipeline then, is it? So let's select it and delete it using the Delete button in the toolbar. Good. Now comes the fun part. What we want to do next is actually add some Python to the pipeline. What we want our Python script to do is augment the output of the pipeline to only return the predicted price. If you remember from our previous demos, the score model module actually outputs the entire dataset and then appends the new column of information that represents the prediction. Well, the consumer doesn't need their whole dataset back, they just need the price. So we're going to add some Python that will do that for us. So let's get to it. Now we want to put the Python script before the output. So that means that we've got to delete the existing connection between the score model module and the web service output module. So let's do that by clicking on the line and selecting the delete button from the toolbar. Now let's move the web service output module downward to make room. And now let's search for the execute Python script module and drag it between these two modules. Good. Now let's connect the output of the score model module to the left input of the Python module. And then let's connect the left output of the Python module to the input of the web service output module. Excellent. Now we have a module that's capable of executing Python against the data coming out of our scoring module. But we want to set what that Python is. So let's click on the Python module to make sure it's selected, and mine is. And now let's click on the Edit Code button so that we can see the code a little bit better. Good. Now I'm going to paste some code in here and then we can talk about what it does. But once again, don't worry, I'll provide the code in the doobly-doo so that you can use it too. Okay, so what we're doing in this code is pretty straightforward. There's a main function that gets executed when the module is run, and that function takes in up to 2 datasets. In our case, we only populate one dataset, the left one, and so we only concern ourselves with data frame 1. If we'd connected to the middle input of the module, then we'd have to use the data frame 2 variable. Anyway, we create a variable called scored results, and we place the values from the scored labels column into that variable. Now remember that the scored labels column is our predicted price. But since that label is not helpful to consumers of the pipeline, we also run a bit of code that renames the column to predicted price. Then the variable is returned from the function. Now it's worth noting that the data type is still a data set. It's just only got a single column in it. Anyway, let's go ahead and save this by clicking the Save button. Perfect. Now we have a pipeline that takes in data from a web service input or manually, does the usual cleansing, though now without the price column, and then applies our model. The output of the model run is then reduced to a single column by our Python script and then sent out to a web service. So let's try it. Let's click on the Submit button at the top of the page. Now the pop-up is asking for an experiment, and in this case, we're going to put this into a new experiment. So let's click on the Create New radio button. And let's give our experiment a name. I'm going to call mine SB Test Demo Experiment Inference. Good. Now let's click Submit at the bottom of the pop-up. Okay, so as usual, the pipeline may take a while to execute, so I'm going to fast forward to when it finishes. Perfect! Our pipeline executed. So let's go look at the results. We can do that by looking at the output of the Python module. Now in the Output tabs, notice that there's a couple of datasets in there. Remember that there are 2 input datasets, so you can flow both of them through. Now in our case, we manipulated the first dataset, so we want to look at the result dataset versus the result dataset 2 dataset. So let's look at that first dataset. Awesome! So now we see a dataset that only has a price column. It has 3 values, one for each row that we sent in manually. It only has one column, and that column has been renamed to represent that it's a predicted price. Fantastic work! In this demo, we're going to deploy a predictive service using Azure ML Studio. To do that, we're going to piggyback off our last few demos and use a built-in deployment mechanism against our existing inference pipeline to create a new endpoint. We'll know our deployment is working if we can access the results externally using Postman. Now first, we need to navigate to the Azure ML Studio in our browser. So in this demo, we're going to piggyback off our previous demos, like I said, where we created an inference pipeline based on a regression pipeline training that we did in demos previous to that. This inference pipeline allows us to predict the price of cars based on a bunch of characteristics of those cars. So let's open the inference pipeline. Click on the designer option in the left-hand menu. Now let's select our inference pipeline from the list at the bottom of the page. Mine was called SB Test Demo Pipeline Inference. Good. So here we are once again presented with our regression pipeline. And once again, I'll do one last recap of what we did here. First, the pipeline takes a data set that is our input, and this can be manual or from a web endpoint, which we're going to do later. The data set is expected to contain a bunch of information about cars. We then use a few transformation modules to cleanse the dataset to something that we can use. The transformers move some unwanted columns and rows, and then normalize a bunch of columns to the same scale so they don't introduce bias in the model training. And the data eventually flows through a few other modules that actually run the data against our model. And the output for the model run is then transformed again using some custom Python that reduces the data to just predicted price. Now the output is then sent to a web endpoint. Now the whole point of this inference pipeline is to be able to predict what the price of cars should be based on characteristics or features of cars given as inputs. In other words, if a user says, "I've got a classic 1961 Ferrari 250 GT California with 2 doors and a 3-liter engine and 240 horsepower, this pipeline should be able to guess that it's worth, $11 million. On the other hand, if a user says, "I've got a homemade go-kart with a 600 horsepower pull-start motor and no doors at all," this pipeline should be able to guess that this isn't worth much at all. Of course, those are extreme examples, and this pipeline probably wouldn't be able to predict those. But hopefully you get the idea. So if we want a user to be able to access our pipeline, the first thing we need to do is deploy it. So let's go ahead and do that. Now on the top right of the screen is a deploy button right next to the submit button. So let's click on that. Now deploying a pipeline means creating an endpoint. An endpoint is a URL that can be used to specifically access your pipeline. So the pop-up dialog here is asking us for details about how we want to configure our endpoint. Now the pop-up wants us to give a name to our endpoint. So let's do that. I'm going to call mine SB Test Demo Endpoint. Next is a description, and this can be useful for Swagger information. Now I would generally recommend setting this value, but in this case I'm going to leave it blank. And lastly, we have the compute type selection. Now, because this is an inference pipeline, we can technically use a Kubernetes service to run our endpoint. And if we leave this section, we're going to be asked to use a Kubernetes cluster to use. But in my case, I don't have a Kubernetes cluster, so instead I'm going to select an Azure Container Instance option. Good. Now our endpoint is ready to be created. So let's go ahead and click Deploy at the bottom. Now the endpoint creation process may take a moment, so I'm going to fast forward a bit here. Good. Now at this point our endpoint exists. Or does it? Let's prove it. To do that, we're going to use Postman to submit a new data set to our deployed endpoint and see what it tells us. Now in order to do that, we'll need some information about our endpoint. So let's click on the Endpoints item in the left-hand menu. Good. Now let's find our new endpoint and click on it to access its details. Perfect. Now a consumer wants to talk to an endpoint, so they'll require 2 bits of information, the URL and a key. Now, both those bits of information can be found in the Consume tab, so let's click on that tab. Awesome. So what we need from this screen is the REST endpoint value and one of the two keys at the bottom of the page. So I've copied those over to Notepad. Great. Now what we want to do is actually interact with our pipeline via this endpoint. To do that, we're going to open up Postman. Now, if you don't have Postman, you can get it for free at postman.com. Now, Postman provides an interface for interacting with any web endpoint. So what I'm going to do here is bring in a request that I've already prepared, but don't worry, I'll provide that request in the doobly-doo so that you can copy it too. First, I'm going to select to import a file using the Import button at the top of the screen. Now I'm going to browse for my file by clicking on the Upload Files button in the middle of the pop-up. Good. It recognizes the file. Now let's click the Import button at the bottom of the pop-up. Now what we need to do is we need to configure this request with a couple of bits of information that it needs. First, you'll notice that this is a POST request, but it's missing the actual endpoint URL. So let's replace the part that says Your Endpoint with the endpoint URL that I copied to Notepad. Good. Now let's click on the Headers tab below the request URL. Now notice that there's an authorization header, and in the header, the value includes a piece of text called Your Key. So let's replace that value with the key that we copied to Notepad. Good. Now before we do anything else, let's quickly take a look at the body of this request. We can do that by clicking on the Body tab below the request URL. Now the body is where we're defining the input dataset. Now pay special attention to that dataset. Notice how there's an inputs object that contains an array called Web Service Input 0. If we were to inspect our inference pipeline, we'd notice that this is the exact name of our web service input module from our pipeline, and this is important. If we called that array something else, this wouldn't work. Meanwhile, inside that array is a single object with fields and values. This object is clearly defining a car. Now the fields match the dataset that's expected as the input dataset. If it didn't match, there'd likely be issues, or maybe the model wouldn't provide any results at all because the row would be removed entirely. Now, this is a demo after all. Real code would protect against this bad input. All right, now let's go ahead and execute the request and see what happens. We can do that by clicking the Send button at the top right of Postman. Excellent! We got a result back. Now let's take a look at that result. Notice that the result object contains a results subobject that itself contains another object called Web Service Output 0. And if you inspected our inference pipeline, you'd notice that's the exact name of our Web Service Output module from our pipeline. And also notice that the value that's returned is labeled just like our Python script asked it to be. Amazing! So now we have a regression pipeline that's trained a model to predict prices for cars. We deployed that model, and then we created a Postman request to access that deployment. In our request, we passed in information about an Alfa Romeo, and our model predicted a price of about $15,000. I wonder if Jeremy Clarkson would agree. That'd be the real litmus test, never mind all this AI business. Anyway, great job. So in this course, we've examined machine learning regression models in Azure. We did this by exploring what regression models are, why they're used, and which are available in Azure, training and selecting a regression model, running the regression model training pipeline, regression model evaluation in Azure Machine Learning Studio, creating a regression model inference pipeline, and deploying regression model predictive services. In our next course, we'll move on to examine Azure Machine Learning classification models.